Hello and welcome to lecture number 4 of the course Advanced Robotics. In the last class, I had discussed about the rotation matrix and then the homogeneous transformation matrix. The homogeneous transformation matrix relates the coordinates of a point which is expressed in a frame that is rotated as well as translated with respect to the reference frame. And today we'll move on to the next part, which is how to assign axis to every joint. And we use the method which was first proposed by Denavit and Hartenberg. So in short, it is called the DH parameters. Okay, so we're going to talk about DH parameters and how to relate one frame to the other frame in today's class. So I discussed in the last class that what we do is we have a fixed base which is not moving, and then we have the links which are connected by joints, and by connecting different links to joints we can have different kind of robots. And what we do is that we assign axis on each of the joints. Say for example, I say this is Z0, Z1, this is my Z2, this is Z3, this is Z4, and this is this is x-axis, this is x0, this is x1, this is x2, this is x3, and that is x4. Okay, now today we'll see how do we systematically assign axis by a method which is basically called the DH notations. Okay, DH parameters. So this name comes from the persons who invented this method, who are Denavit and Hartenberg. Okay, and hence in short it is called DH parameters. Now the method is very simple, but we need to assign axis very systematically. Now the first thing is number one, the z-axis. The z-axis is the axis of rotation or translations. So z-axis is the axis of rotations or translations. So if it's a rotation axis, means it's a revolute joint, then it's a rotating axis. If it's a translating joint, a prismatic joint, then it's a translating axis. Now the z-axis is the axis of rotation or translation. So when I drew my z-axis, you saw that now this is a planar manipulator. Let me draw it again and explain. So this is a planar manipulator, so please follow this very carefully. For simplicity, let's consider this to be consisting of two links only, just for simplicity. Okay, so I have maybe two links and an end effector there. So the z-axis is the axis of rotation. Now if you can imagine, the axis of this is pointing out of the plane, and this link can move like this. Okay, this manipulator can move like this, right? But it is always on the plane, right? So this is a revolute axis, that is also a revolute axis, and that is a revolute axis. What does this mean? The axis of this revolute joint is pointing out of plane. So the z-axis is the axis of rotation or translation. In this case it is rotation, so the z-axis will be like this. Okay, this is my z-axis, that's my z-axis, and that's my z-axis. They're all pointing out. Okay, so this I can call Z0, the reference frame which is not moving, and the first axis which is connected to the first joint is 1, second one is 2, and third one is 3. So z-axis is the axis of rotation or translation. That's rule number 1. Rule number 2 is x-axis is the shortest distance between the z-axis. This also is easy to understand. So where is the first x? The first x0 can be anywhere because it's a reference frame, so my x0 is here. Then the next x is the shortest distance between the z's. So what is the shortest distance between z1 and z2? It is the perpendicular distance, so this is my x1. Similarly, between z2 and z3, this is my x2, and that's my x3. Okay, so we have assigned our x-axis and our z-axis. Now in case the z's are intersecting, then x is perpendicular to plane containing z's, to plane containing z-axis. Okay, so this is a subgroup of assigning x-axis. So it says that the x-axis is the axis, x-axis is the shortest distance between the z-axis. But in the case the z-axis are intersecting, in this case they are not intersecting, they are all parallel. Okay, so there is no problem. But in the case the z-axis are intersecting, then x is perpendicular to plane containing z's. Okay, what about the y-axis? Y-axis is as per right hand rule. So x, the moment x and z are fixed, y gets automatically fixed. So in robotics we don't draw y-axis because as per right hand rule y is already fixed. Okay, so this is the very simple way of assigning an axis. First is, let me repeat, z-axis is the axis of rotation or translations. That's very easy. Next is x-axis is the shortest distance between the z-axis. Okay, and in the case z's are intersecting, then x is perpendicular to plane containing z. So let me look at this, the second part once. Take an example where this is happening. For example, we look at this manipulator. So I have a manipulator like this. Okay. There is another link which is, let me say there is a link here. And this link can move front and back. So that's my link number 2. And there is link number 3 which is connected here to the end effector. Okay, and this let me say this can rotate about this axis. Now this contains a revolute joint. Which is the revolute joint? If you can imagine, it can rotate about this axis. So that's a revolute joint. Okay, that's a vertical axis. So my revolute joints at 0 and 1 are given there. 0 is the reference frame which doesn't move. The first axis is 1. Okay, next is, which is the second axis. The second axis is a translating axis. Now this link is a translating axis here. So it can come this side, it can come forward. If you can imagine, this can go forward like that, or it can go back like that. So it's a translating axis. Okay, that means my z will be along the direction of translation. So this is my z2 now, because it is z2 is red color is fixed on the red part. Okay, so if you can imagine, this red part is like this. Okay, this is one end. So my z2 is here actually. Okay, which is on the red color part, which can move front and back. Okay, so this is my translating axis, so it can move front and back. And what about the third one, which is the maroon color? So this is, it can rotate about that axis, so that's my z3. Okay, so what we are seeing is that this is a 3 degree of freedom system, and there are 3 axes. It's a revolute, prismatic, revolute system. Okay, prismatic axis is the red color one, which is moving from right and left. Okay, now here we have put our z-axis, z0, z1, z2, z3. Now I have to put my x-axis. Now you note here that the z1 and z2 are intersecting. Okay, so they're intersecting here. Z1 is here and Z2 they're intersecting at that point. So x is going to be perpendicular to plane containing z's. Is perpendicular to plane of z's. So what is the plane of z? The plane of z is this one. So x is going to be perpendicular to that. So x is here. So let me say x0, x1 and x2 are that side. Okay. Now what about x3? x3 is here. Okay, so now we see that we have assigned our x-axis and our z-axis. Okay, we start off with z and then we assign our x-axis. This is a case where the z's are intersecting. In the previous case, the z's were all parallel, so this problem was not there, so x was easy to assign. Okay. Now this is a very nice looking manipulator. So now let's look at a generalized case, and what we want to find is what is the number of transformation requires to go from one frame to another frame in 3-dimensional space. Okay, so let us look at a 3-dimensional case, and we can have all kinds of funny shapes. So let's say the manipulator is like this. Okay, this is a manipulator, and this is the shape of the link. So it's like this. Okay, so this is a manipulator which has any shape, which has a 3-dimensional shape, and 3D it can be any shape. So that is why I'm drawing it this way. Okay. So you can imagine that this is an axis. Okay, so this is, there is a previous link on this side. So the shape need not be a very nice straight line. It can be having any curve, and it can have any shape in 3D. Okay. Now how do we start? Let us start by z-axis, assigning our z-axis. Z-axis is the axis of rotation or translation. Now this is a revolute joint. So this is my z-axis. Okay, so let us call this axis my zi minus 1. I minus 1 basically means the previous axis. So if this one is I minus 1, the next axis is going to be I. Now if you say this is I, then the next will be I plus 1. Okay, it is simply to say that if this is 1, the next is 2. What about the next one? The next one is here. So that's my Zi. These are axes of rotation. Next, I have to assign the x-axis. Now, where is my x-axis? Now, let us say that the shortest distance between these two axes is given by this line here. Okay, this is the perpendicular distance here, and this is the shortest distance between the two lines, between the two axes. Okay, so this is perpendicular here. So I say that xi minus 1 is the shortest distance between them, so it is xi minus 1. Okay, what about the other xi? The other xi is here, so I can call it here and say it is along that side. So this is xi. Now y we don't care, so y is going to complete the right hand rule. If you want to draw, then y can be that side, so that's yi minus 1. And this side also there is a yi minus 1, yi. We don't normally draw I. Okay. Now the question is, how many transformations are required to take you from frame? So the question is, how many transformations are required to go from I minus 1 frame to I frame? Okay, that's the question. So if you look at this, because there are 6 degrees of freedom in three-dimensional space, it would appear that you need 3 translations, 3 rotations. But Denavit-Hartenberg were the first persons to explain that if you assign your axis like this, the z-axis is axis of rotation or translation, x-axis basically is the shortest distance, then they showed that you don't need 6, but you need less than 6, which is 4. So which are these 4s? Let us see. So the first thing that we do here is I draw a line which is parallel to this. So this is my, so what I'll try to do is I will align axis I minus 1 with axis I. How many transformations are required? So the first thing I do is I draw a line which is parallel to this. So this and this are parallel. Okay. So what I do is I move my xi minus 1 axis by an angle alpha. So what happens, my zi minus 1 comes here. Okay. So I move it by an angle alpha. So now what happens, zi minus 1 is parallel to the next zi. What did I do? I moved with an angle alpha. Next what I do is I move, so next what I do is I move this origin from here to here, okay, by a distance ai. So first is an angle, let's call it alpha, let's call it a, let's call it a1. Then what I do, now my axis has come here. So if you can imagine, your zi minus 1 is here, your xi minus 1 is this side, xi minus 1 is there. Okay, so the zi and the zi minus 1 are aligned. Now xi minus 1 and xi are not aligned. Okay, so what I do is next I rotate xi by an angle theta, and take it xi minus 1. So this is now aligned to this. So there's a small angle theta there now. Okay, so now the x's are aligned, the z's are aligned, but the origins are still different. So what I do is I moved it by a distance theta, alpha a theta. Then what I do is I move it by a distance d. So I move the origin from here to there, it goes there by a distance d. Okay, now they're all aligned. The origins are the same. The xi and xi minus 1 are aligned. Zi minus 1 and zi are aligned. So how many transformations were required to align two axes in three-dimensional space, which can be in any direction? So there are 4. The first is alpha, then a, then d, then theta. So this alpha is called the link twist. Okay, this is called the link length. This is called the link angle, and this is called the link offset. This is called the offset. So these are 4 parameters, and these 4 parameters are called the DH parameters. Okay. So how are they defined? Let me just go through this again, because this is a little tricky to understand, but once you understand it, there is no problem. So we have, let me draw it again here. Okay, so this is a link which is having any shape, and this is the next link. The next link is in that direction. Okay, so the first thing that we do is assign your z-axis. How did we assign our z-axis? Z-axis is axis of rotation or translation, so my z's are here. Okay, then what we did is, so this is given as zi minus 1, that is zi. Then I put my x-axis. Where is the x-axis? This fellow's x-axis is here, and we find the shortest distance between these two z-axis, and I put my x I minus 1 along that side. The next one, xi goes there. So now I'm saying that I want to align the two axes I minus 1 with I. So how many transformations are required? So what do? We first rotate. We draw a line which is parallel to this, the other axis. So this is parallel to this. I move this by an angle alpha. Okay, so there's an angle alpha. Then what I do is I move it, the origin, by a distance a. So I move it here. That's the distance a. Now what has happened? My zi minus 1 has come here, and my xi minus 1 has I minus 1 has come here. Okay. Now what we do? So I have had alpha, then we had a, then I have theta. I rotate this and make it align it there. I have angle theta. Now this is aligned to this. Then I move it upward. I move the origins such that the origins go up by a distance d, and the origin comes here now. That's d. So I had 4 transformations: alpha, a, d, alpha, a, theta, and d. Okay. So how are they defined? A is the distance. So a is the distance from zi to zi plus 1. Okay, it is, we can say this is the distance, let's call it, let's say it's the distance between the z's. Distance between the z-axis measured along the x-axis. Okay, so what is a? A is the distance between the z-axis. There was one z here and there's another z here, and a is the distance between them measured along x-axis. That's my a. This is also called the link length. Alpha is the angle between z-axis. So it is the angle between z-axis measured along x-axis. Okay, so alpha is the angle. So this angle is, this is the angle alpha. It is measured about the x-axis. So this angle is the angle between the z-axis, which is measured along the x-axis. So we have a alpha, then we have d, a alpha, d, and theta. So d is the distance between the x-axis along z-axis. So this is the distance d. So we are measuring the distance from here to here as d. So is the distance between the x-axis. Okay, so one x is here, that's the other x. So is the distance between the x-axis along the z-axis. And what is theta? Theta is the angle between x-axis along z-axis. Okay, so these are the 4 DH parameters, and this is how they are defined. A is the distance between the z-axis along x-axis. Alpha is the angle between z-axis measured along x-axis. D is the distance between the x-axis, okay, measured along the z-axis, and theta is the angle between x-axis measured along the z-axis. So whenever we have a manipulator, before we write the kinematic chain, we need to find the relation between these two, between two axes. Okay, and we need to see what is the relation between them, and they're related by these 4 parameters: a, alpha, d, and theta. Okay, let's take a very simple manipulator. So from here, what we need to do is we need to make a very simple DH parameter table. Okay, and from the DH parameter table, we are going to systematically write down the transformation matrices, and using the transformation matrices, multiplying them out, we are going to go from one frame to another frame. So let's take a very simple example. The simplest example which we can get is this one. Let's say it's so here let me draw a planar manipulator like this, and like this. Okay, so this is a 3R, okay, 3 DOF manipulator. Okay, now let me say the link lengths are L1, L2, and L3. Okay, these are the link lengths. Now let's assign our DH parameters and write down the DH parameter table using the DH conventions. So here your z-axis is axis of rotation or translation. Please note this is 3R revolute joint, so the axis is pointing out of the plane. So this is my z0 and z1 for the first one. 0 does not move, and the z1 is fixed to the first link. This is my z2 and this is my z3. Okay, now we have fixed our z-axis. Now let's fix our x-axis. what is the x-axis? The first x, we keep it horizontal. It can actually be anywhere. The second x is the x distance between the z-axis. So the distance between z1 and z2 is x1. z2 and z3 is x2, and this is my x3. Okay. Now let us write down the DH table. So we have to write down the DH table, parameter table, and then derive the matrices which the relationship between any two frames. So in the DH table, we write it this way: A, alpha, D, and theta. Okay. Now how many joints are there? This is my first joint, second joint, third joint. So first joint, second joint, third joint. So this basically gives me the relationship between frame 0 and 1, 1 and 2, 2 and 3. Okay. So this is my frame numbers. Now A is the distance between, is the distance between this z-axis, right? This is the angle between z-axis. This is the distance between x-axis. This is the angle between x-axis. Okay. So now if I start defining, A is the distance or the link length between the z-axis of which two frames? 0 and 1. Now 0 and 1 are at the same point. They have the same origin. So there is no distance between them, right? So Z0 and Z1 is the same axis. So there is no distance. So it is 0. What about the angle between the z-axis? Z0 and Z1. Again, there is no angle. They are the same axis. So it's 0. What about the distance between the x-axis? Now the two x-axis, x0 and x1, are meeting at the point, at the origin. So there is no distance here. It is 0. Now, what is the angle between the x-axis? That is theta 1. So if this manipulator were to move, it can move this side like this, like this, like this. What has changed? This angle has changed. Okay. So the angle between the x-axis is the one that changes. Okay. And hence it is called the link angle. So this is called the link angle. And this is the one that changes. What about the relation between frame 1 and frame 2? Now, where is frame 1? Frame 1 is here and frame 2 is there now. So A is the distance between the z-axis. What is the distance between the z-axis? It is L1, which is the link length. Okay. What about the angle between the z-axis? Z1 and Z2 are parallel, so it is 0. What about the distance between the x-axis? Now x1 and x2 are intersecting at the point. They are intersecting in the origin of frame 2. Okay, so this is my 0. Now if link 2 moves, what will happen? Link 2 will move like this. So what has changed? This angle has changed. Okay, so this angle basically has changed. So basically this is my theta 2. So when a link moves, what happens? That link angle theta changes. That's what we're seeing here. Now what is the relation between frame 2 and frame 3? Again, the A is the distance between the z-axis, which is L2. Alpha is the angle between the z-axis. They are parallel, so there's no angle. What is the distance between the x? Now x2 and x3 are intersecting at the point, origin of frame 3. They're intersecting, so there's no angle. And when link 3 moves, what happens is it goes this side or it goes this side. So what happens? This angle changes, and that is my theta 3. Okay. So this is what gives us the DH parameter table for this manipulator. Okay. Now what do we do with this? I need to find the transformation matrix between each of these frames, and then I can find the total transformation matrix between frame 3 and frame 2. Okay. So what is the transformation matrix between frame 1 and frame 0? It's a homogeneous transformation matrix. Just to revise what we had done in the last class, the homogeneous matrix okay, is a 4x4 matrix in homogeneous space, and it is defined this way, that if you have a fixed frame like this, so this is my x, y, and z, okay, and you have another frame which is rotated and translated. So the other frame is rotated and is translated by some distance. Okay, so this is my BP. Okay, so this is my frame A, that's my frame B. So what is this matrix T A to B, which is going to relate B to A? Actually, this is my x dashed, y dashed, z dashed. Okay, so basically what we do is we complete this vector equation and we write our matrix, which comes out of the form. This part is the rotation matrix, rotation between A and B. This is the del x, del y, del z is the distance moved by, or the distance between the origins of frame B and frame A in the x direction, y direction, and z direction. And this is 0, 0, 0, and that's 1. Okay, so this is the one that gives us the relationship between two frames. Okay, in this case it is B with respect to A. So going back, I have to find what is the first matrix T. Let me say there are three transformation matrices. This one is T0 to 1, then there is a T1 to 2, and then there is a 1, 2 to 3, right? So let us write down the matrix and see what it looks like, and then we'll find a way of systematically writing it. T0 to 1. Okay, so if I write this matrix, let us write it this way. This is always 0, 0, 0, this is always 1. Now look at frame 0 and frame 1. Okay, here when they rotate, there is only one variable, theta 1, which is going to change. So, and it's a rotation about z axis. Okay, now if you are thinking why the z was the axis of rotation or translation, that is essentially to simplify our computation, because these rotations are always about z. Okay, so that the matrix is the same. So in this case it will become cos theta 1 minus sin theta 1. This is sin theta 1, this is cos theta 1. Okay, this is 0, 0, 1, this is 0, 0. Okay, that is the rotation matrix between these two frames. Which two frames? 1 and 0. Okay, because they are the two frames, if you can imagine. Let me just draw it here. One frame is here, z0, z1, this is x0, and x1 is here. Okay, and where is y? y0 is here, y0 is here, and y1 is here. So it's a rotation about z, and it's a rotation about z by an angle how much? Theta 1, that is theta 1 now. Okay, and what is the transformation matrix? Rotation about z, if you remember, our z theta is equal to cos minus sin cos 0, 0, 1, 0, 0. Okay, and that is how I get this now. What is the del x, del y, del z here? That is the distance between the origins. Now the origin of frame 0 and that of frame 1 is the same, so there is no distance between them, and hence it is 0, 0, 0. Okay, now what is the second one? The second one is 1 to 2. Okay, so what will be this matrix? So this matrix is going to be 2 to 1. Okay, what is this matrix going to be? So look at the frame 2. Frame 2 is here and frame 1 is down here. Okay, now what is the rotation between them? Rotation is again rotation about z. Okay, about this is rotating about z axis. So this is going to be the same, cos theta 2 minus sin theta 2, sin theta 2 cos theta 2, 0, 0, 1, 0, 0. It's a rotation about z axis. What is the distance between the origins? Now the two origins are different. What is the distance between them? It's L1. L1 in the direction of x, and hence N1 will come here. There is no distance in the y, so it is 0, this is 0. This is always 0, 0, 0, this one. Okay, I hope you have. There is a more systematic way for writing this matrix easily. I'll just come to that. This is just to explain how we write our transformation matrices. This is 2 and that is 3, and 0, 0, 0, this is 1. Now look at the frame 3 and the frame 2. Okay, the origins are not same. Z2 and Z3 are parallel, and there is a distance between them. So when the frame or the link 3 moves, what will happen? It moves, it rotates about the Z3 axis, and theta 3 will change. It's a rotation about Z. So it is cos of theta 3 minus sin theta 3, 0. Sin theta 3 cos theta 3, 0. That's 0, 0, 1. What is the distance between them? There's a distance of L2 in the x direction. So this is the transformation matrices. So these are the three matrices. Now if I want to multiply them out, 0 to 3, I'm simply going to multiply 0 to 1, 1 to 2, and 2 to 3. The order is not changed, the order is the same because we are in homogeneous space now. Okay, so this matrix will give me the total matrix between the third frame and that of the 0 frame. Okay, so what is the first thing that we do? And let's take an example again. So the other example that I gave, let me draw that again. So this is these are just examples of different kinds of manipulators. So this is a 3 degree of freedom. This is a 2R1P robot, and this is the second joint. The second joint is here. Okay, that's the second joint, and this is the third joint. So this is continuous like this. Okay, so let me go back and draw it there for clarity. Yeah, so this is actually dashed line, means it is going through. Okay, now it should be clear. So let us draw this now. And where is the third? The third is the gripper. So let's say there is a gripper here like this. Okay. Now we are going to assign our frames. Let us assign our frames like this. The first frame we're going to assign is the z-axis. So z0, z1 is here, z2 is there, and z3 is here. Okay, we will assign our z-axis. Next, let's assign our x-axis. Now the x-axis is the z1 and z2 are intersecting. So our x has to be this side, x0, x1 and x2. Okay, and because they are in this side, we put our x3 this side. Okay, now let's let us assume that there is a distance from here to here. The distance from here to here, it's let's call it a distance d2. Okay, now I have taken the origins of 0, 1 and 2 here for convenience. The 0 and 1 origin could have been here like this, that's also okay. Okay, but then a distance here will come then. Okay, it doesn't matter, it has to be considered in the DH table. I'm just simplifying it by saying that the origin is here now. Now let's write our DH parameter table. Let's look at this carefully and write A, alpha, D and theta. So initially when you are doing it, so it's 1, 2, 3. This between 0 and 1, this is 1 and 2, this is 2 and 3. Initially when you're writing the DH parameter table, it's a good idea to write down that A is the distance between Z, this is the angle between Z, this is distance between X, this is angle between X. Okay, now let's start off by writing A is the distance. So between frame 0 and 1, they are the same, z-axis is the same, right? So the origin of frame 0 and frame 1 is the same, and hence there is no distance between the z-axis. There is no angle between the z-axis, because if you look here, z0, z1 is the same axis. Similarly, there is no distance between the x-axis. They're intersecting, they're the same axis. This is 0, so this is my theta 1. Okay. Next, what we can do is we look at the relation between frame 2 and frame 1. Now frame 2 and frame 1, only the z is different now. Okay, so z2 is horizontal, z1 was vertical. What is the distance between the z-axis? There's no distance because they're intersecting there. So this is 0. Now what is the angle between z? There's a 90-degree angle there. So it's like clockwise 90 degrees, so it's a minus 90. So clockwise is taken as minus, okay, rotation. So it's like you're standing from here and watching. Okay, this is where you are and you're watching, and this is clockwise. Okay, and that is how we define our clockwise here. So the clockwise rotation of 90 degrees, so z1 was this direction, it has rotated and become z2 clockwise by 90 degrees, so it's minus 90 there. What is the distance between the x-axis? So x0 and x1 and x2 are the same axis. This is important, that when the link 2 moves, what happens? This link goes this side. That's the red color one. So the origin of 2 also moves with the link. So this is my, let me draw it in red color. So if you look at the link 2, it's like this. Okay, and there is another link here like this. So the origin is here now. This is my z2 and this is my x2. Okay, so frame 1 and frame 0 are fixed onto the black color body, whereas the frame 2 is fixed on the red color body. So when the red color body is translating, what is changing? The distance between the origin of frame 2 and frame 1 is changing. Okay, so if it moves on the right side, frame 2 will come here now. Okay, this will become z2, this will become x2. What is changing? This distance, and that is my d2. So that is a variable which is d2. There is no angle there, so it's 0. Okay, I hope you understand that when the red color link moves on the right side or the left side, what changes? The distance between x2 and x1 changes, because the origin of frame 2 and frame 1 will change now. Okay, and that is my variable which is here. This is the variable in the case of a translating joint. What about frame 3? Frame 3 is fixed here. So what is the distance between the z-axis of frame 2 and frame 3? Z-axis are along the same line, so it is 0. Okay, because they are along the same line, it's my 0. What about the angle between the z-axis? There is no angle because they are along the same axis. Okay, they are along the same line. Now what is the distance between the x-axis? There is a distance of d2 here, so I put, sorry, let's call this, if that's my d2, let's call this L2, otherwise it will confuse. So let me put this as L2. So the distance between the z-axis, so z2 is here and z3 is there, so this is my L2. Okay, and what is the angle when it rotates like this? What will change? Theta 3 will change. So that's my DH parameter table. So using this DH parameter table, we can actually make the transformation matrices. I'll show you how. So what we need to do is to make T0 to 1, T1 to 2, and T2 to 3. Okay. Now let's look at another example of the manipulator to understand how do we assign our frames. So in this case, let's look at the example of another manipulator which looks like slightly different. So this manipulator is this one. Okay, and I hope you can visualize this, and there is a link here also which goes in like that. Okay, now let us try and visualize this. Now it's very important that you should be able to visualize. So when this rotates, what happens? This is a 3 degrees of freedom, and this is 3R, okay, 3 revolute joints. So this is my first revolute axis. Let me mark it here. This is my first revolute axis. This is my second revolute axis, and that's my third revolute axis. So I say this is my z-axis is the axis of rotation here. So Z0 and Z1. This is Z2, and that is Z3. Okay, these are the 3 axes of rotation. Now you should be able to understand, visualize that how we are getting this 3 axis, and when it moves, what happens. Okay, so now let's so we have put our z-axis. Now we have to put our x-axis. Now x-axis for the first one, again note that Z1 and Z1 and Z2 are intersecting axis. Okay, and hence there is a 90 degree there. So it will mean that your x-axis will be coming outside x2. Now since x2 is coming that side, we put Z0 and 1 also that side. X0 and x1 also along that. And here is my x3. Okay, so we have finished our x-axis. Now please note what are the various lengths which are there. There is a length here, there is a length between this axis. Okay, let's call this L2, and there is a distance between, so this axis between here and here, there is a distance there. Let's call it D2. Okay, I hope it's you can visualize what these distances are. Now let's write a DH parameter table: A, alpha, D, and theta. So this is 1, 2, and 3. Now the first axis and the 0 axis are here. They're the same axis actually. So everything is 0 here, 0, 0, 0, theta 1. So when this manipulator moves like that, what will happen is the angle between x1 and x0 will change. So x0 will be fixed always, right? It cannot change. It's a fixed axis. Only x1 can go that side, or x1 can come this side. Okay, it can go that side or this side on that plane. Okay. So this is my first axis, which is rotating, which is 0, 0, 0, theta 1. Now, where is the second one? The second axis, just for convenience, I've taken the origin of 2 and 1 to be the same point. I could have taken origin of 2 here, okay? But just for convenience, I've taken it here. Now, because the origin of 0, 1, and 2 are the same, 2 and 1 are the same, then what is the distance between the z-axis? The z-axis are intersecting, so there's no distance. What is the angle between the z? Now the angle is 90 degrees because it is a rotation 90 clockwise, okay, about the x-axis. So again, as I said, you can imagine yourself standing here and then looking in that direction, okay, towards the origin. Then clockwise is considered negative. Now then what is the distance between, so this is what is the distance between, so this is distance between z, this angle between z, distance between x, angle between x. What is the distance between x? Now x2 and x1 are the same, so there's no distance, so there is 0. And when it rotates, what will happen is it goes up and down like this. So this angle will change here between x2 and x1, so that's my theta 2. Okay. Now look at frame 3 and frame 2. Now if you look at frame 3 and frame 2, then we see that the origin of frame 2 has moved like this, and then it has moved like that. It has come this much distance d2, then it has come L2. Okay, so what is the distance between the z-axis? The distance between z-axis is L2. Okay, now what is the angle between the z-axis? Z2 and Z3, they are parallel, so there's no angle. Now what is the distance between the x-axis? So this small distance is there because x3 is here, okay, along that side, and x2 is here, so there's a distance of d2 here, so this is my d2, and variable is theta 3. So this is my DH parameter table for this manipulator. Okay, so what we are seeing is that we have to assign axis properly to be able to figure out which is the correct way of assigning an axis, and then write down the DH parameter table. Now, from taking each row of this, we can write the transformation matrix and multiply them out, and then get the relation between the last frame and the base frame. Now, there is a systematic way of doing that, and if you write a computer program, then there is a generalized matrix, and the generalized matrix can be used to get the generalized to get the transformation between any two frames. Okay. Now here we have seen that there is basically three transformations. One is alpha, then is A, then is theta, and is D. So there are two. This is a rotation, that's a rotation, this is a translation, and this is a translation. So if I multiply all four of them, I get one generalized matrix which considers two rotations and two translations. Okay, so what you do is you write down the rotation matrix for this, write down the translation matrix for this and this, multiply them all out, and we'll get the generalized matrix, which will generate anything to n plus 1 matrix. Okay, and that matrix is has this form, it has this structure. Let me write it down. So the generalized matrix T I minus 1 into I is given by cos theta minus sin theta 0 AI. Then we have sin theta cos alpha, cos theta cos alpha minus sin alpha di. Oh, let's not use the word, let's not use the subscript I. A and D is good enough. Then we have sin theta sin alpha, cos theta sin alpha, and this is cos alpha. This is cos alpha into D, and this is 0 0 0 1. Okay, so cos theta minus sin theta 0 A, then sin theta cos alpha, cos theta cos alpha, sin alpha D, and then it is sin theta sin alpha, cos theta sin alpha, and cos alpha D 0 0 0 1. How did we get this? We had four transformation alpha A d theta, so we multiplied each of these transformation matrices, and this is the generalized one we get. So if I take the generalized matrix, and from the DH parameter table I take each row and put it inside here, I will get the respective transformation matrix. That is the use of this. So in a computer program, this is how we make our respective matrices. Okay, so what I'm trying to explain, let me do it here. So we talked about our two-link manipulator, which was like this, and like this. This was our two-link manipulator. Okay, 3DOF 3R manipulator. Now for this, we had made our DH parameter table, which is this one. I'll write it very quickly again. So this was our DH parameter table, if you remember this one. Okay, so I'll write down the DH parameter table again. It is same as this. Okay, and then we will derive our transformation matrices, which is T0 to 1, 1 to 2, 2 to 3, using the generalized matrix. Okay, so let me very quickly write down the DH table of this. So I put Z0, Z1, I put Z2, I put Z3. Okay, this is my X0, X1, X2, and X3. This is L1, L2, and L3. So L1, L2, and L. Okay. Now we have written down our DH parameter table. Let me write down the DH parameter table very quickly. A alpha d theta. So A alpha d theta. Let me write it down very quickly. 1, 2, 3. Okay, and this is 0 0 0 theta 1, this is L1 0 0 theta 2, and this is L2 0 0 theta 3. You can cross verify with that. Okay, now I want to make my transformation matrix. So the first transformation matrix is going to be T0 to 1. Now this matrix is going to be, this is 0 0 0 and that is 1. Okay, that will always be the same. So let me take one row at a time. Let me take this row 0 0 theta 1 and put it in here. Okay, what will you get? So there is only one variable theta 1, everything else is 0. So it will get cos theta 1 minus sin theta 1. Okay, here you will get sin theta 1 cos theta 1, because cos alpha is cos 0 is 1, cos 0 is 1. This will become 0, and this is 0, that is 0, and that is 0. Okay, so I take the first row and I put it in there. What will I get? I'll get cos theta 1 minus sin theta 1, sin theta 1 cos theta 1, 0 0 1 0 0. Okay, what is A is 0, what is D? It is 0, so this is 0 0 0. I hope you understand what I have done. I've taken the first row. So in the case of a computer program, we have a generalized matrix like this, and then we make the DH parameter table, which is an array, which is a matrix basically. And what the program will do, it will take one row at a time. It takes one row at a time, puts it in the generalized matrix, and it gets the first matrix. Then it takes the second one, puts it in there. So what is the second one? 1 to 2. This is the second matrix. This will always be 0 0 0 1. Okay, next is, there is a distance L1 here, and there's a variable theta 2. Now if you look at the variable theta 2, so it's a cos 2 minus sin 2, cos 2 minus sin 2, sin 2 cos 2, 0 0 1 0 0. All you need to do is take this row, second row, and put it into that matrix. And then what we do is, there is a distance, so A is there. So what is A? A is equal to L1. Okay, what is sin alpha? Alpha is equal to 0, so sin alpha is equal to 0, and D is also equal to 0, right? So this is 0 and that is 0. This is my second matrix I've got. What about third one? 2 to 3. Okay, 2 to 3 is going to be like this. Okay, so 2 to 3 is going to be, take the third row, put it there. So this is 2 to 3, this is 1 to 2, and this is T0 to 1. Okay, so this is 0 0 0, that is 1. Now in the third case, what is the variable? So theta 3 is the variable. What is L2? L2 is the link length. So what we do is, I take the third row and I put it in there, and what we get is cos 3 minus sin 3, sin 3 cos 3, 0 0 1 0 0. What is the del x, del y, del z? There is only one. A is only L2 is there, so there's L2. D is 0, so it is 0 and 0. Okay, so this gives us the three matrices which we had derived some time back. So if you just go back and see the three matrices that I had written, the three matrices are the same matrix that we wrote here. Okay, and so if I multiply them all together now, I'll get the relationship between the third frame and the 0 frame now. Okay, now let's do that and see how it goes. So let's look at these three matrices. Okay, and multiply them out. So let me multiply the first one, T0 1 into T1 to 2, which is equal to cos 1 minus sin 1, sin 1 cos 1, 0 0 1 0 0. This is 0 0 0, and this is 0 0 0 1. What is T1 to 2? It is cos 2 minus sin 2, sin 2 cos 2, 0 0 1 0 0. So this is 0 0 0, and this is L1 0 0 1. Okay, what do we get? We get, if I multiply this into this, you can see it is cos 1. So let me, cos 1 cos 2, okay, minus sin 1 sin 2, which is equal to cos 1 plus 2, theta 1 plus theta 2. So I'm writing it short in cos 1 2. Okay, in short. So the first term that we're going to get is going to become cos 1 2 minus sin 1 2, sin 1 2 cos 1 2. This is 0 0 1, this is 0 0, this is 0 0 0, and this will become cos 1, or rather L1 cos 1, and the second is going to become L1 sin 1. This is 0, that is 1. So this is my matrix. t 0 to 2. Now I have to multiply this into the third one, so it is t 0 to 2 into t 2 to 3. So I'm writing my 2 to 3 matrix here. So this is cos 3 minus sin 3, sin 3 cos 3, 0 0 1 0 0 0 0 0, and this was what, L2 0 0 1. So if I multiply them out, what you get is t 0 to 3, which is equal to cos 1 2 3. Please multiply them out. So this into that will become equal to cos theta 1 plus theta 2 plus theta 3 minus sin theta 1 plus theta 2 plus theta 3. This is sin 1 2 3 cos 1 2 3, 0 0 1. This will become L1 cos 1 plus L2 cos 1 2, L1 sin 1 plus L2 sin 1 2. Okay, you can multiply it out, and this is what it will be. So cos 1 2 3 means cos of theta 1 plus theta 2 plus theta 3. Okay, this is what it means. Now, so this is the matrix which relates the third frame to the zero frame now. Okay. Now, if you're wondering how did I write it so quickly, am I copying from somewhere, or and also whether it is correct? Okay. Now, if you simply look at the manipulator, look at the structure of this equations. Look at the structure of this matrix. This is the rotation part. This is the translation part. This is always 0 0 0. This is always 1. Okay. So the structure is maintained. So is it correct? Now, if you look at the manipulator, let me just draw it. Let me draw the manipulator here. So this is my L1, L2, L3. So this is my theta 1. This is theta 2. That is theta 3. So if this is my x-axis, that's my y-axis. Z-axis is the same. This is Z0, x0, y0. So where is the third frame? The third frame is here. This is my Z3. This is my x3. So I want to relate this matrix T0 to 3 relates the third frame to the zero frame. Okay, so this matrix that I have got, is it correct? That's the question. Okay. Now if you look at this side, this is the distance del x, del y, and del z. So distance between the origins along x-axis, y-axis, and z-axis. So is that correct? So if you look at this here, if I project it down here, okay, this is my theta 1, right? So what is this distance? This is del x, which is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, which is correct. So this is L1 cos 1, and this is L1 cos theta 1 plus theta 2. This is my theta 1 plus theta 2, right? What about the y direction? Y direction is del y, which is equal to L1 sin 1 plus L2 sin 1 2. Okay, so del x and del y, what we have got, del x and del y is correct. Okay. In the z direction, it doesn't move because it's planar, so it's 0. Okay, so this is correct. What about the angle? So if you look at x3, x3 is here, x0 is here, this x0, that's x3. So what is the total angle between x0 and x3? So it is theta 1 plus theta 2 plus theta 3. So the total angle about rotation about z-axis is cos 1 2 3 minus sin 1 2 3, 0 0 1. This is sin 1 2 3 cos 1 2 3, 0 0 1. That's the total rotation about z. Okay, so if you go back and see again, if you just go back and see, this is the rotation about z. So we have got it. Okay, so it shows that it is correct, because when we go back in the manipulator, it actually we can verify this. Please understand this very clearly. So instead of doing all this, I could have actually simply looked at the manipulator. I could have written the matrix also. Okay, because once you understand the homogeneous transformation matrix, it's very easy to correlate and then to write. Okay, so today we will stop here. So what I want you to really understand and comprehend is that what is the structure of the manipulator. So what I want you to really understand is what is the structure of the homogeneous transformation matrix. And by looking at a manipulator structure, you can actually write down the final relationship between the last axis and the zero axis. Okay, because the structure remains the same. The rotation matrix is the sum of all the rotations, and the del x, del y, del z is the distance that the origins have moved in the x, y, and z directions. So we'll stop here today. Thank you.